Okay, so let me first thank the organizer for inviting me to give this talk in real life. So my title is Structure of Jackiw-Teitelboim Gravity Boundary Correlation Functions, and my talk will be roughly based on these papers and some work in progress. So let me start by giving you a brief outline of my talk. So of course, I'll first give you an introduction to what Jackiw-Teitelboim gravity actually is. And then I will specify to the JT boundary 2-point function. And in particular, I will emphasize its description in terms of the Schwarzian theory and the perturbative treatment of that. And then I will present two different perspectives on this model, or in particular on this boundary 2-point function. The first one coming from a gauge theory perspective, because Jackiw-Teitelboim gravity can be rewritten in its first order formulation as an SL2RBF model. And using that perspective, I will give an exact treatment of these boundary correlators, and I will also discuss a special class of these that you can understand better from this gauge theoretic perspective. And then secondly, I will give a string theory perspective, a string theory embedding of Jackiw-Teitelboim gravity within Liouville gravity and the minimal string. And in particular, I will emphasize an interpretation in terms of a quantum group deformation of the group theoretic structure of ordinary JT gravity and some lessons we can learn about higher topology. So first, let me start by giving you an introduction. So there have been many developments in lower dimensional gravity, and in particular in Jackiw-Teitelboim or JT dilaton gravity in 2 dimensions. And much focus in the past few years has been on spectral properties, in particular the partition function, the spectral form factor, to exhibit chaotic features of bulk black holes. And in particular, people have studied very extensively during the past couple of years, higher genus and multi-boundary amplitudes, which have been shown to be very important to understand the very late time behavior. Also replica wormholes to better understand the black hole information paradox and so on. But in this talk, I want to focus on correlation functions of local boundary probes. And in particular, I want to sketch an exact quantum solution of these boundary correlators. So this was studied, also during the past 5 years, roughly in these papers. And the emphasis of this talk will be on their structure and their relation to other solvable models. Now, they are also very interesting because they have an interpretation or an interesting interpretation in terms of bulk gravitational physics that I will not be talking about. So you can take a look at these papers to find out more. In particular, you can relate the out-of-time order correlators to shockwave scattering in the bulk close to the black hole horizon. You can learn lessons about bulk reconstruction, complexity, and so on. But I won't be talking about these bulk gravitational interpretations. I will be talking about the structure of these correlation functions. Okay, so now Jackiw-Teitelboim gravity, what is it? So it's a specific model of 2-dimensional dilaton gravity, which was proposed by Jackiw and Teitelboim in the 80s. Its action, which I've written down here. So it's a dilaton gravity model where the Ricci scalar couples to the dilaton field phi. And there's a dilaton potential, which is linear in phi, which I've written here. So lambda times phi. And then if we study this model on a manifold with a boundary, we need to add a Gibbons-Hawking boundary-like term, which I've written down here. So this parameter lambda has the interpretation, of course, of a cosmological constant. And if I pick lambda to be negative, so -2 in the conventions of units that I have chosen, then this will be describing asymptotically ADS spaces because I want to be studying holography. Now, in 1+1 dimensional gravity, there are no local degrees of freedom. There are no bulk gravitons that appear. So the bulk is topological. But with the suitable choice of boundary conditions, you can get an interesting dynamics at the boundary. And the boundary conditions that I will impose, so, I won't go into the technical details, so I refer to the papers for the actual argument. So the boundary conditions are at the holographic boundary. And I demand that, the metrics over which I'm going to path integrate will all be asymptotically Poincare, and also that the boundary follows a constant and large value of the dilaton field phi. Now, if you impose these boundary conditions on these models, it turns out that the description is fully in terms of a dynamical holographic boundary curve whose dynamics is described by the Schwarzian action, which I've written down here. So the Lagrangian itself is the Schwarzian derivative. So to be very explicit, here is the expression. And there's a coupling constant, the Schwarzian coupling constant, big C, which is proportional to 1 over the 2D Newton's constant that we started with. So the dynamics is fully reduced to a boundary dynamics in terms of a single degree of freedom that we have here, f of tau, which you can think of as a dynamical time reparametrization of the boundary curve in terms of some proper time tau. Now, this derivation that I roughly sketched here is to be compared to the way you think about 3D Chern-Simons theory on a manifold with a boundary, where the boundary dynamics is governed by the 2D WCW CFT. Because also in that case, there would be large gauge degrees of freedom, where A mu is G minus 1 D mu G, would be identified with the physical degrees of freedom G in the dual WCW model. So we have the same setup here, large diffeomorphisms that would, that would not leave the boundary invariant. They are physical and they correspond precisely to these dynamical time reparameterizations.
Excuse me, there's a question in the chat.
Yeah, sorry. You say lambda is a cosmological constant, but usually lambda is just a coefficient in front of square root of minus g without the dilaton. So, and if you add this term, it should be a slightly different model, a richer model. You cannot just eliminate this term.
You're absolutely right. There is also another model where you won't have that lambda multiplying the dilaton field phi. But as you can see here, for instance, if you take, or if you look at the equations of motion, if you vary with respect to phi, you get R equals lambda.
Of course, that's of course, but cosmological term for me is just lambda, not phi lambda.
Yes, but okay. Yes. So it's just a matter of words, I think. So maybe I shouldn't call it cosmological constant. It's sort of a modified term in the dilaton potential.
Absolutely. And I think that cosmological constant is simply not introduced here.
Yes. Okay. Strictly speaking, I agree with you.
Mm-hmm. Okay.
Okay. So now that we know that Jackiw-Teitelboim gravity can be rewritten in terms of dynamics of the Schwarzschild theory on the boundary, I want to study correlation functions in this model. And for that, I will transfer to the thermal theory to study thermal correlation functions. And I will obtain boundary correlators by doing this type of path integral. So this is the thing that I want to be thinking about. So I have a path integral over the Schwarzschild degree of freedom. So I have e to the Schwarzschild action that I had on the previous slide. And I have an arbitrary number of insertions of operators that depend on some parameter h1 and so on. I will specify what these operators are in the next slide. Now, there are some technicalities here. So I have introduced, well, the big F we had on the previous slide, but also a small f. They are related by this tangent transformations. And well, there's a technical identity for the Schwarzschild derivative you can write down. The reason for doing that is that this small f of tau is now to be interpreted as a dynamical reparameterization of the boundary circle, so of S1. In particular, it satisfies these two conditions. So well, f dot is always positive to be a valid reparameterization. And if you go once around the proper time circle, you go once around the f circle. So the picture that you have here is, which I've drawn here. So in red is the holographic boundary. We path integrate over the quantum gravity fluctuations in the middle here in green. And I've drawn on the boundary in blue a specific example of a clock ticking pattern for some off-shell choice of f of tau, some reparameterization of this boundary clock. And that's what we're path integrating over. There's also a non-trivial measure and so on, but I'm not going to go into the details of that here. So this is roughly what we want to be calculating. Now, what are these operators? It turns out that there is a very natural class of operators to consider in the Schwarzschild theory, which are bilocal operators. So they depend on two times, tau1 and tau2, and they're given by this, this combination of the function f of tau that we're path integrating over. So f dot tau1, f dot tau2 divided by f tau1 minus f tau2 squared, raised to some power h, where h is some real number. So these operators are parameterized by that number h. Now, where does this come from? Well, first of all, you can view this as a reparameterized boundary CFT two-point function. So reparameterized by the function f of tau. And that is, by doing that, coupled to the dynamical time variable f of tau itself. A second way, perhaps a way that one might like more, is that you can also interpret this as the result of a world-line path integral of a scalar particle of a mass m squared related to h in that typical way, that is being emitted and reabsorbed at the boundary at times tau1 and tau2. So if you just do that auxiliary world-line path integral, you would automatically get this bilocal operator. So this is a second way of thinking about these operators. This is a natural operator to be considering, and inserting one such operator in the Schwarzschild path integral will describe a boundary two-point function in this model. Now, there's still the question, how do you actually compute anything with this action? because the action is very complicated. It has a Schwarzian derivative in it, so that it's a higher derivative action, so it doesn't look simple to do, well, at least a priori, to do anything with it. Now, the first thing you might try is to do perturbation theory. So I expand f of tau in terms of its saddle and fluctuations, and if you try to find the saddle, you just find f of tau equals tau. So you write f of tau equals tau plus epsilon of tau, where epsilon is, of course, a fluctuation. This fluctuation needs to be periodic then. You plug it back in the action, as I've done here, and then you find, of course, the quadratic term, and then a whole array of higher order terms in this epsilon expansion that would describe the vertices. So this is an interpretation in terms of the boundary graviton degree of freedom epsilon of tau and their interactions. Now, just to be a little bit more explicit, to show, or at least to sketch you how a calculation like that would go. So, well, the first thing you do is you distill the propagator from this quadratic piece. The propagator scales as 1 over c. And well, I've just shown you here the explicit expression, which is relatively complicated. And then there are vertices, which I haven't written out explicitly here. So of course they come from these higher order terms and they all scale like C. And then you also need to expand the operator in this epsilon expansion. So all of these bilocal operators. So I've done that here for one operator. So you can see explicitly where the epsilons appear. And you need to Taylor expand this in epsilon again, and then contract the different epsilons with the propagators and so on. I think it is. No, wait, where? I'm actually not so sure at this moment. Yeah, it's a good question. I you know, you're right. It doesn't look periodic when I write it like that. I'd have to check. Maybe we can talk about this later. I definitely know that this is the correct answer. If you do calculations with it, it works. But yeah, good question. Well, okay. In any case, so these are the propagator vertices and the operator, and this, of course, then leads to a perturbative expansion in 1 over c. And 1 over c, if you remember, is the Newton's constant. So this gives you an expansion in the Newton's constant of any type of correlation function you might want to compute. But this is actually very complicated. Not at lowest order, but at higher orders, this expansion becomes extremely involved because there are more and more vertices coming from the Schwarzian action, and because, well, I didn't mention this in detail, but there's a non-trivial path integral measure. So this perturbation series is very hard to actually keep track of beyond, for instance, one loop order. So we'd have to, or it would be more interesting to find another way of calculating these correlation functions. And this is the first perspective that I want to give you on these types of correlation functions, which is from a gauge theory perspective. So it is well known also since the 80s, so roughly the same time that Jackiw-Teitelboim wrote this model down, that the first order formulation of this gravity model, at least without boundaries, is given in terms of an SL2RBF gauge theory. So now we need to include boundaries because we have holographic boundaries. So, well, to simplify matters, let's first study the case of a compact group GBF model and see what we get. And then we will generalize to the case relevant for gravity. So let's write down a 2D BF gauge theory on a manifold with a boundary. So I've written down the BF action, so it has a B field and F, which is the curvature term associated to the gauge connection A. And then when I have a manifold with a boundary, I write this boundary term with this specific boundary conditions in order to have a good variational principle. Now, if you imagine you insert this action in the path integral, the first thing we would do is we would path integrate out the bulk field B here, because it just appears as a Lagrange multiplier. It forces the connection to be flat. So A equals G times dG minus 1. The bulk term is completely gone at this point. So we just insert this in the boundary term and we get the action of a particle moving on the group manifold G. So we just get the dynamics only at the boundary given by this action. Now, the structure of this theory is well known. So first of all, the Hilbert space is fully determined by the Peter-Weil theorem. In particular, it is spanned by these eigenstates which are labeled by going through all the unitary irreducible representations of the group G, and A and B, which are indices that run through each of these representations. So this is the representation basis. And they diagonalize the Hamiltonian, as you can easily show, because the Hamiltonian is just the quadratic Casimir in this representation. Now there's a second basis that is useful, which is some sort of coordinate basis where you just take the group elements as the states, and they have a non-trivial overlap with these representation basis cats that is given, up to a factor square root of the dimension of the representation by the representation matrix element, RAB, as a function of G. So now, as an example of a calculation you can do with this model, you can do exactly with this model. And also, of course, because this will be the precise calculation that we will need to generalize to go to JT gravity, is we will consider the disk amplitude with a boundary anchored Wilson line on it. So we want to do the BF path integral on this disk, and I have in blue here this boundary anchored Wilson line that I inserted in my amplitude. And to evaluate this, we will time slice this as propagation, as I've shown already in the picture, between these 2 points here, where I insert the identity group element. You propagate from the left here, you encounter this Wilson line, and you propagate further until you reach this point. So using this time slicing, you can write the amplitude in this way, where this W here is the Wilson line insertion. Now, to evaluate this, you would insert a complete set of states in the group element basis, as I've done here. And that way, the Wilson line just becomes a representation matrix, as I've written here. But then you need to diagonalize, of course, the Hamiltonian to make to do the calculation. So you would insert complete sets of states in the representation basis, which you can do, and then you can simplify things using, of course, this overlap that I mentioned previously, and this group integral that you automatically reproduce, where one of these R's that appear. So this is an integral of a product of 3 representation matrices. One of these was coming from the Wilson line insertion, and 2 of these are coming from the states that you insert, the complete sets of states that you insert. And this group integral is well known. It's just a product of 2 3J symbols. And plugging that all in, you find a relatively concise expression for this amplitude. So it has a sum over the 2 representations, R1 and R2, the product of 2 of the dimension factors, 2 Hamiltonian propagation factors, which are weighted here by the Casimir in the 2 representations, and then the square of a 3J symbol. And it is this 3J symbol that couples these 2 sums together, that couples the R1 and R2 together. So this is the structure of this amplitude for a single boundary anchored Wilson line for any compact group G. Now, the structure of these amplitudes might be familiar because it is well known from 2D Yang-Mills. And in fact, they are identical to the amplitudes you would write down in 2D Yang-Mills. The only difference being that 2D Yang-Mills is sensitive to the areas of the sectors of the diagrams, whereas this model is sensitive to the boundary lengths. So for 2D Yang-Mills, there would be an A1 and an A2 instead of tau and beta minus tau here. Okay, so now let's go to gravity. So I will be relatively sketchy here because there's lots of technicalities and subtleties that appear here. But what you need to be doing is that you get gravity from the SL2R group element, but there needs to be an additional constraint at the holographic boundary, a gravitational constraint, which you can parameterize in this way. So A tau equals B was the boundary condition we had for any compact group. But now, in addition, I constrain that form to be of this way, at least if I write it in the fundamental representation of SL2R. So there's zeros on the diagonal and a 1 here. And this last entry is arbitrary. And I choose to write it, with hindsight, of course, already as the Schwarzschild derivative of something else. So these are the additional gravitational constraints. And with these constraints, you can see that you can make contact directly with this Schwarzschild description, because if you plug this ansatz back in the particle on the group G action, you immediately get that the Lagrangian just becomes the Schwarzschild derivative of this parameter f, or of this function f that I introduced here. And simultaneously, if you plug this ansatz into the boundary anchored Wilson line, but now in a suitable representation and a suitable state within that representation, so the choice you have to make is the lowest weight state of the discrete infinite dimensional representation. After some calculations, you find that this boundary anchored Wilson line precisely becomes a Schwarzschild bilocal operator. So I've shown you here just from staring at the path integral, so both the operator insertions and the action, that indeed, if you pick suitable boundary anchored Wilson lines for the SL2R case, you indeed just reproduce the starting point of the Schwarzschild calculation. So this calculation will match with the Schwarzschild calculation, except that now we will be able to do it explicitly. So for the actual amplitudes, so we just need to generalize the calculation that I did earlier, which required these representation matrix elements and these 3J symbols and so on. So we just need to generalize that. So again, it's a bit technical. So let me just give you the final result. It turns out that the Hilbert space is spanned by constrained matrix elements. They are constrained because of the gravitational boundary conditions. And the constraint means that you have to evaluate these matrix elements in what is called a mixed parabolic basis, and then you constrain these parabolic indices. So these are all technicalities that you can ignore. That makes these matrix elements Whittaker functions, and they can be written very explicitly in terms of Bessel K functions with an index 2ik and an argument e to the phi. So what is all of this information? So what is K? K labels the continuous irreps of SL2R with Casimir K squared plus a quarter. Secondly, as I mentioned, these gravitational constraints, they restrict this representation index to, well, I call it 0 here. So instead of having arbitrary indices here, they are constrained by the gravitational constraints at the holographic boundary. And then what is phi? Phi is one of the coordinates on the SL2R group if you use Gauss coordinates. So I refer you to these papers if you want to know the technical details of that. Secondly, we had dim-R appearing in these well, compact group calculations. The role of that is the Plancherel measure on these continuous sets of representations, which in this case becomes k times sinh 2 pi k. And then finally, the Wilson line insertions, the operator insertions. As I mentioned on the previous slide, you should pick the lowest weight state of suitable representations. And then, well, you just need to look at the literature to find what it is. And it's just an exponential function in this phi. Now, well, if you believe all of this, then what you should be doing now is calculating this 3J symbol, because that's the main non-trivial thing that enters in these calculations. So you do a group integral of the product of 3 representation matrices. The group integral reduces to just a single integral over phi here because of these gravitational constraints again. You get 2 of these representation matrices associated to the states, and one of them associated to the Wilson line. So this is just this integral of the product of 3 representation matrices that is giving you 3J symbols. It's just that there's a bit more detail here, these gravitational constraints and so on, that make it technically a bit more involved, but morally it's the same kind of calculation. And this integral is elementary. You can do it and it gives you this result. So in the numerator is a product of 4 gamma functions. So that's what I mean by the plus minus symbols here. And then you divide by gamma of 2h. So putting it all together, this is what we find for the JT gravity boundary 2-point function. So you get 2 integrals over these representations, these continuous representations, K1 and K2. You get the Plancherel measure for both of them, playing the role of dim-R. You get e to the minus, then the boundary length times the Casimir, which is, well, K squared. And the same one for the second representation. And then here, the square of the 3J symbols. So that is the result you get for the boundary 2-point function. So the result for inserting a single of these bilocal operators in the Schwarzschild theory. Now, there are other approaches that give you the same result. So I'll just mention them here, so I won't go into detail. You have a 1D Liouville approach. There's also 2D Liouville between identity branes, a particle and magnetic field, and also an approach from the minimal string or Liouville gravity, which is something that I will talk about later during this talk. And the important point is that all of these other approaches agree, and they find exactly the same boundary 2-point function, but we have explained it here, or we have explained the different ingredients from a group theoretical perspective. So now that we have this answer, let's analyze or at least mention some of the perturbative properties to make contact again with this perturbation series expansion that we had in the beginning. So I reinstate the Schwarzschild coupling big C in this expression. So previously I suppressed that. So it just appears here in these exponents. And then you can show that if you do a 1/c expansion of this expression, that it agrees with the perturbative approach that I mentioned at the beginning. So perturbation theory and the Schwarzschild theory, at least what can be checked. And then, well, what is particularly interesting, I think, is that the 1/c expansion here can be shown to be asymptotic only. So that means that there is non-perturbative content in these exact expressions that go e to the minus something divided by 2D Newton's constant. So this expression is going beyond perturbation theory and boundary gravitons, and it would be interesting to learn of a direct physical intuition, which, well, I don't know the answer to this. But there is an exception to this analysis, and that is when 2h is a negative integer, because you can see here, that's when this gamma function is blowing up. That would bring the entire correlation function down to 0. So the correlation function would naively be 0 unless it gets compensated by something in the numerator. So unless there is a relation between k1 and k2. So that will mean that this entire integral reduces. So it starts out as a 2-dimensional integral over k1 and k2. Then it becomes a 1-dimensional integral, so somewhat simpler. So let's analyze this case in a little bit more detail. So what we actually need to do is we need to redo the derivation of these 3J symbols, because in this case, they would correspond to Wilson lines, again, in lowest weight states, but in other representations, in the finite dimensional representations of SL2R, where I use the spin label J, which would be minus H. So these 3J symbols are not these gamma functions now. They are, you can write them explicitly like this. So there's a sum over an additional index M. The most important point is that there's these delta functions that indeed enforce a relation between the two K labels that we had previously. And well, of course, this makes the answer simpler, because you now only have one K integral to do instead of 2. And because of that, this allows you to investigate these perturbative expansions in a bit more detail. So it's easier to analyze them. And in particular, what you can show is that now this 1/c expansion becomes convergent. So the full story you have is, so I draw the real line here, the real H line, is that this series is always asymptotic except at these blue crosses where it becomes convergent. So then you have a real expansion in only boundary gravitons, and that's it. Also, just a curiosity here, you see these binomial factors that appear here in these sums. They match precisely with the binomial expansion you would do of the bilocal operator itself, because in the numerator here you have f tau 1 minus f tau 2 to the 2j, and 2j would be an integer. So you write down the binomial expansion and you find precisely these factors. So this is just curiosity here. So these are special kinds of operator, or special bilocal correlators that require a separate treatment, but they are structurally simpler. So you can exploit them to learn lessons about the perturbation theory in particular. Okay, so now during the last part of my talk, I want to give you a different perspective on these correlation functions, which is to embed them in a string theory perspective. And in particular, I will embed them in Liouville gravity. So let me first already mention the results that we will find. So the structure of these correlation functions in Liouville gravity will look like Q-deformed results of the ones you would find in JT gravity, the ones we had up to now. And also the higher genus worldsheet expansion you would do in string theory gets reinterpreted in terms of a multi-universe expansion. So let me first give you the definition of the model that I will be studying, just for clarity. So I will be talking about the non-critical string you get by coupling a 2D matter CFT to gravity, or the critical string with Liouville matter and ghost CFT coupled together with total central charge equals 0. So the action is just the sum of the Liouville matter and ghost action with the conformal anomaly vanishing. Just to be very explicit, I write down the Liouville action here in terms of the Liouville field phi. It's parameterized by this parameter mu, which is the bulk cosmological constant, and this parameter b that is defining my Liouville theory. Conventionally, of course, as usual in Liouville theory, you introduce big Q, which is b plus 1 over b, and then the Liouville central charge is 1 plus 6q squared. You can imagine, if you're coming from 2D gravity, that this arises from a conformal factor in the metric. So if I can parameterize any two-dimensional metric in this way, where the conformal factor is the only dynamical degree of freedom, and that the dynamics is governed by Liouville here, and g hat is just some reference metric. Then we also have a matter piece, the matter action, and for most of this, the rest of this talk, it will be just an arbitrary CFT with central charge less than 1. But in a couple of slides, I will specify to the minimal model, the Q, P minimal model, in which case this becomes the minimal string. And then, of course, we have the usual BC ghost theory. Now, because I will be interested in making contact with these calculations in this Liouville gravity with JT gravity, I will be interested in holography. So I will be interested in 2D manifolds that have a boundary of fixed length, because those are the calculations that I was doing in Jackiw-Gravity, where we have fixed length boundaries. Now, how do you do that in Liouville or in Liouville gravity? So for the Liouville piece, you do this by introducing first introducing an FCCT-Braim boundary, which means that you add this boundary action to the Liouville piece. It's parameterized fully in terms of the boundary cosmological constant mu b that is specifying the specific FCCT-Braim you're studying. And then when viewing this theory as 2D quantum gravity, as I mentioned already on the previous slide, the Liouville field is related to the metric by just a conformal factor here, which means that the boundary length computed in this metric is just a line integral of e to the b phi. And then, well, it becomes relatively easy to compute fixed length amplitudes because in the path integral, you just do a Fourier transform in mu b. So you integrate over mu b along an imaginary axis, you multiply by this exponential factor. And because mu b only appears in this boundary action in a linear way, this just brings down a delta function, setting this line integral v to the b phi equal to the parameter L that we introduced, which gets the interpretation, of course, in terms of a boundary length. There is a generalization that I will use where we just pick piecewise constant mu b, and then you do this Fourier transform for each of these pieces, and then you get a boundary with fixed length segments. So now let's apply this to the case where we will be able to make contact with these calculations in Jackiw-Gravity, which will be the boundary 2-point function in Liouville gravity. So what we will consider is two boundary tachyon vertex operators in this string theory model, which you get by addressing a matter primary field that I call phi m, conventionally with the Liouville MBC Go. So this is just a standard thing you would write down in string theory. So these are the boundary tachyon vertex operators in this model. I add two of them at the boundaries of this disk, and I separate them by fixed length segments. So what is the amplitude of this calculation? So we start out by, well, looking at the literature and finding the Liouville boundary 2-point function, which is known, and it's written, well, up to prefactors, it's written here. So there are these there's a product of 4 double sign functions in the denominator here. S1 and S2 are labeling the FCCT-Braim boundaries in this way. So the S labels are related to the boundary cosmological constant this typical way. And now we just need to transform this thing to the fixed length basis for both mu b1 and mu b2. So 2 times, we have to apply the Fourier transform 2 times. And after some calculations, this is the expression you find. So it's an integral over S1 and S2. There's 2 densities that I call ρ0 here, which are both sinh times sinh. There's an e to the minus L1 cos 2 pi b S1, and the same thing for L2. These are these Hamiltonian propagation factors. And then there's this ratio of SB functions, 4 of them in the numerator, 1 in the denominator. So this expression has a very similar structure to the one from Jackiw-Gravity.
Sorry, it's just a clarification. I didn't understand what was this SV function.
Read this. Oh, it's a double sign function. It's a special function that you always get in these Q-deformed.
Double sign function.
It's called a double sign function. I haven't given you the details. I won't need the details. The only thing that I will need is how it's related to the ordinary gamma function. I will mention in a second.
Thank you.
Okay, so as I mentioned, this structure is very similar to the structure we had of the boundary 2-point function at Jackiw-Gravity. And indeed, there is a nice JT limit where you set B to 0, so B was the Liouville parameter, and you scale the other parameters in a suitable way with B. And then you use this specific limit of the double sign function, how it relates to the gamma function. And then you find precisely the JT answer that we had previously. So there is a limit to go to Jackiw-Gravity here. And of course, because the structure is so similar, it's no surprise that there is also sort of group theoretical interpretation of all of these ingredients in this amplitude. And the statement here is that the Liouville gravity amplitudes arise from, well, constrained version. By constrained, I mean, again, the gravitational boundary conditions of the modular double of the Q-deformed SL2R quantum group, where the deformation parameter Q is e to the pi IB squared, where B is this Liouville parameter. So this is a lot of words. So let me just briefly explain how this works. So this structure here, this quantum group structure, has a set of continuous so-called self-dual irreducible representations. So again, I'm omitting the details here. studied by Ponceau and Teschner and many others since then. And in particular, these representations have a Casimir operator. So the representations are labeled by an index S, and you can write the Casimir operator as cosh 2 pi bs. So that will be the energy variable, and that's the thing that appears in these exponents here. And these representations have a Plancherel measure, which is sinh times sinh, which is precisely the densities of states that we had here. So we only need to check that this last thing can be interpreted as some sort of 3J symbol. And for that, we need to do that integral where we insert the product of 3 representation matrices. So in particular, we need this special mixed parabolic matrix element, or this Whittaker function of this Q-deformed SL2R group. And this was obtained in this paper 20 years ago in a very different context, in the context of a relativistic Toda chain. And this is the answer that they write down. So it's relatively complicated. It has an integral with more of these SB functions in it. The details are not important. What is important is that this thing leads to the correct 3J symbols. If you do the integral where you take 2 of these complicated functions here, you insert them twice, and then you insert this exponential function here, which would represent this, the same as this Wilson line, basically. You can do that integral and you precisely find this ratio of double sign functions, again, matching this thing here. So this shows that this Liouville gravity calculation has a quantum group interpretation. Okay, so up to now, I just picked an arbitrary matter CFT with central charge less than 1. Now let's specify to a specific matter CFT, the minimal model, such that the total thing would be the minimal string. Now this minimal string has only primaries coming from the degenerate matter Virasoro representation. So the matter sector is degenerate, and what I called beta m. So let me go back to the previous slide. Beta m was the entry that was appearing here. So it was playing the role of the H, let's say, of the Wilson line. So this beta m is now restricted to be of this form for 2 integers n and m. So it's restricted to be an element of a finite discrete set. Now you can check that precisely for these choices, this SB of 2 beta m, which was the denominator in these previous calculations, is precisely evaluated on its poles. So again, the correlator seems to become 0 unless the numerator also vanishes. And again, your 2-dimensional integral, your integral over S1 and S2, would reduce to an integral over just one of these S parameters. So this is very similar to what we had in JT gravity. Now, if we further specify to the 2, p minimal string, these beta m labels are even more simple, and you can write them as minus b times a half integer. And in particular, so if you then try to do the calculation, try to find what replaces this ratio of double sign functions, the Liouville boundary 2-point function itself, which you started with, can be rewritten in terms of elementary functions here, so in terms of just cosh functions. And then you just do the transform to the fixed length basis again, and you find after some calculations this expression. So it looks relatively complicated here, but you can see that it only has one of these S integrals instead of 2. And in particular, so this complicated expression, if you now take the limit again, the JT limit where b goes to 0 and the other parameters scale in a suitable way, these boundary tachyon vertex operators, they limit precisely to these special operator insertions that we had in JT gravity. So these are like the ancestors of these special operators in JT gravity corresponding to finite dimensional representations of SL2R. But now they're coming from the only primary operator insertions you would have in the minimal string. Due to this origin in the minimal string, these special operators form an integral subclass of operators in JT gravity, whereas all of the other operator insertions, where H is not a negative half integer, are outside of this class. Okay, so in the last couple of minutes, I want to briefly mention some things about going to higher topology. So everything that I mentioned now was for the disk partition function where you have a Wilson line in. So how do higher genus corrections work for this boundary 2-point function? So we first go back to JT gravity. And this was studied in particular for the partition function, multi-boundary amplitudes, and the spectral form factor in this famous paper by Seitschenker and Stanford a couple of years ago. And their main conclusion was that JT gravity as a whole is a matrix integral. So how does this work when you add these boundary operators? So how does this work for correlation functions? So there's a general expectation that higher genus corrections only correct the density factor in these correlators. So this is motivated by ETH for sufficiently simple operator insertions, but let me just mention what this statement means. So in all of these integrals, we had row 0 of, well, K1 and K2, I call them. So K1 and K2 are related to the energy, so we can just write this in terms of the energy variables as well. Row 0 of E1, row 0 of E2. We just replace this by the pair density correlator in the random matrix ensemble that is supposed to describe JT gravity. And this is supposed to capture all of the higher genus corrections. So this motivation is coming from ETH and from a random matrix theory perspective, not necessarily at this point from a bulk gravitational calculation where we add higher topologies. And this pair density correlator, you can write it, well, as you can always do in random matrix theory, as a disconnected piece plus a connected piece. Now, the question is, how do you reproduce this form from geometry, from considering higher topology contributions? Well, there are two rules that you can follow that give you the right answer in the bulk geometry. So imagine you start with a disk where you have a single of these Wilson lines in it. The first thing you should do is you should cut the surface along this Wilson line, so you get two of these disconnected pieces. And then you should add higher topology in all possible ways to this cut surface. And there are two different classes of higher topology you can consider. You can consider disconnected pieces on both sides of this line, or you can consider a connected piece where these two sides are geometrically connected. Of course, this matches with the previous or the random matrix result, where the pair density correlator is also written as disconnected plus connected piece. So they match with these geometrical pictures. And you can show that you indeed reproduce the full answer from a bulk gravity calculation. So I'm not going to do that here. I'm just sketching you the rules because I want to mention a specific puzzle that you have if you follow these rules. Because at first sight, you imagine you just need to add all possible forms of higher topology or higher genus corrections to this genus 0 answer. But these rules actually include some things, because to reproduce this random matrix result, we assume these Wilson lines do not self-intersect in the bulk by, for instance, wrapping, let's say, the base of a handle. So by following these rules, I'm excluding the case where, for instance, this line would wrap around this handle here and then go to the other side. These cases are excluded because I first cut along this line to begin with. So why is that? Can we understand why these specific lines should be excluded here? Now, we will use the embedding in the Liouville gravity or in the minnow string, where the calculations are in principle well understood. Now, higher genus corrections, where there are boundary operators at play, we don't have enough technical control to actually give the answer. So I will start with a simpler amplitude in the Liouville gravity, which is the bulk boundary 2-point function, again in the fixed length basis. So now we're again in the Liouville gravity, or in the string theory perspective. We have a single boundary operator and a single bulk tachyon vertex operator. So I add the details here, but they're not important. You can transform this thing to the fixed length basis. You get something like that. And then you can take the JT limit again. You get something like this. The details are again not important, but you can interpret this in a diagram as a single Wilson line that starts and ends at the same point, and it wraps some sort of defect here, which is the remnant of this bulk operator, but it wraps it once, only once. In particular, there are no multi-wound paths that are produced in this calculation, in this limit from string theory. And these multi-wound paths, those would be the ones that would be self-intersecting. The singly wound path is not self-intersecting. So this was all for a bulk operator, but well, I skip all of the explanations here, but it can be shown that higher topology, you can get this by gluing tubes onto these defects that we have here. So this is actually sufficient to show that indeed no self-intersections need to be considered when you consider these higher topology corrections, or well, at least it points towards this direction. And we have found this conclusion again by taking the JT limit from string theory. And in the string theory perspective, no Wilson line is drawn in the first place. So there is no ambiguity. We just compute this amplitude. It's only in the JT limit where we want to draw these Wilson lines and we get confused by which types of configurations we should be considering. So embedding this in string theory seems to resolve this issue. Okay, so let me conclude. So I analyzed several structural properties of boundary correlators in JT gravity. In particular, I mentioned the exact solution on the disk for the boundary two-point function using this gauge theoretic BF perspective. There's a special class of correlators where h is a negative half integer that have a simplified structure. In general, the perturbative expansion of all of these boundary correlators is asymptotic only, except for these special cases where it's convergent. I have embedded this JT gravity story in Liouville gravity and a minimal string, which from a group theory perspective can be viewed as Q deformations of JT gravity. And in particular, these special kinds of correlators we had in JT gravity, they arise from a limiting procedure from these minimal string tachyon vertex operators. And then in the end, I analyzed several aspects of the higher genus expansion. So to conclude, JT gravity is part of an intricate web of exactly solvable models. So I mentioned, of course, the BF model and the minimal string here, but it's also closely related to 3D pure gravity just by dimensional reduction, and then to 3D Chern-Simons and so on. And in this web of models, JT gravity and the Schwarzschild model have not been studied in the early literature, only in the last couple of years. And the hope of all of this is, of course, to leverage this knowledge of these exactly solvable models to learn more about quantum gravity, as we have been doing in the past couple of years. So thank you.
Okay, thank you. Now we have time for questions. So first, we're going to take questions from Matthias.
Hey, thanks for this very nice talk. So if I understood correctly, JT gravity you can think of as this BF theory based on SL2R. And then it seemed to me that Liouville gravity you should be able to interpret as the BF theory based on UQ SL2R.
Yes.
Is there a way in which one can sort of expand on this? And I mean, you seem to sort of getting it by virtue of the fact that this calculation looked like the UQ deformation of the other, but can you write this more explicitly
the
as
hope.
an action? Or
that would be the hope, to understand it more explicitly from a Lagrangian perspective, for instance. But at the moment, we only seem to understand it from the explicit amplitudes. Yeah, but that would be very interesting.
So can I follow up? So these 3J symbols, you got them by these integrals. By these 3J symbols, one can also get by studying repeated tensor products and using. So I assume the answers you get are compatible with that perspective, or could you also derive them directly from that perspective?
So you're talking about the Q-deformed case now, or
either of them?
Well, it is just group theory, so it should be consistent. We just calculated, or we found them in this case in our calculation in the form of an integral of the product of three representation matrices. So that is well what the exact calculation is doing. But this is just group theory, so it has to be consistent.
But I mean, could this be a simpler way of deriving them? I mean, that you just sort of use the self-consistency of the tensor product decompositions to. Well,
maybe, but we have already found them at this point.
Sure, I mean, I'm not disputing that you found them, just asking whether.
Yeah, maybe.
And for this for the Q-deformed things, there are usually these special things that happen with indecomposable representations and stuff that you have to truncate. Is this sort of built into this?
Sorry, which kind of representation?
I mean, for the for the Q-deformed quantum group representations, there are always these funny rules that you have to truncate the spectrum at some place, at least for the compact case. So UQ SU2, only a certain finite number of representations appear, and then you get some truncation at this level. Is there something you see for that for UQ-SL2 or?
Well, the representation that played the biggest role here were just these continuous representations. They form the states. So they're continuous and there is no truncation for those.
Even in the UQ case?
Even in the UQ case. That's, for instance, these integrals over S, they were just from continuous, well, they were integrals from 0 to infinity that go through all of these representations.
Okay.
For the operator insertions, you can try to think about how to interpret that in terms of representation theory of discrete finite representations, for instance, of UQ-SL2.
Questions?
Hi. It has been claimed that Jackiw-Teitelboim gravity can be described also at the final cutoff. Okay, and in that case, it seems that is related to a sort of T-bar deformation of the Schwarzian theory. Is it possible, in your opinion, to derive this result starting from some kind of deformation of the Liouville theory?
To start from what?
From the Liouville perspective, I mean, or for the two-dimensional perspective.
So to have a finite cutoff version for the
Sorry. Okay.
to have a finite cutoff version directly for Liouville gravity.
Yes, because I mean, the one-dimensional, the JT can be described by a sort of TT bar deformation.
Yes.
So I have in mind some very simple idea that you can maybe deform by some TT bar like deformation, reveal, or minimal string, or whatever you want, and then go down to the JT.
To do it purely in Liouville gravity in this language, I think we need more control. We need to better understand these things from the Lagrangian perspective. So I've just presented the results in terms of the amplitudes, but yeah. So in particular, this Liouville gravity, so there are arguments you can give to reinterpret this in terms of a dilaton gravity model, but instead of a linear dilaton potential, it would have a hyperbolic sine dilaton potential. Hyperbolic sine, well, is literally also the thing you would find in the algebra that Q deforms SL2R to Q deformed SL2R. So you need to understand, or I think one needs to understand better this perspective from the dilaton gravity point of view. And yeah, so that's still to do, I think.
Okay, thanks.
So a bit related to Matthias's question, so sometimes the spatial truncation appear when a Q is a root of unity in particular, as opposed to real or something else. So do you see anything? I mean, does this?
Not for the states. So the representation that were important for the states were these continuous self-dual representations. They don't have anything special happening when Q is a root of unity. But for the operator insertions, you might argue that there is something happening. And in particular, if you specify to the 2, p minimal string, and p is an odd integer, and you know that q is e to the pi I b squared, and b squared is is just the ratio q over p, then that is precisely the case where q becomes a root of unity. But for at least for the things that I mentioned here, the states themselves, they don't see anything. There's nothing happening there.
Thanks.
Do we have more questions from the audience? Yes.
I would like to ask about the asymptotic nature of the expansion in 1/c. So you had these non-perturbative objects, and I'm just wondering if you know the physical origin, whether they correspond to instantons or a normal one.
Yeah, that is an open question. Yeah, I mentioned that. Well, from a technical perspective, you can see that the series is asymptotic, so there should be more than boundary gravitons. But I have no intuition for these objects what it might be, or whether there's a nice physical interpretation of these things. I would be interested in knowing that. Yeah.
So you cannot construct a sort of trans series yet, which would give back the full integral.
Well, I didn't try that. Maybe you can. I don't know.
Okay, thank you.
Okay, more questions from the audience? Okay, if not, we have a question from Zoom.
Hello? Do you hear me?
Yes.
Yes.
Please, I wanted to ask you, can you solve say a more complicated model like TJ gravity also coupled to 2D gravity, I mean, containing the fluctuations of the metric, not just the delta functional, not the delta functional condition, but say you relax the fluctuations. For example, you add the Gaussian term to the dilaton field. I know that people solve such models with conical singularities, and in principle, if you take a gas of conical singularities, you can also have fluctuations of gravity on the background of constant negative metrics.
Yes, to get to other.
How far can you go? Mm-hmm.
So you mean to get to other dilaton potentials, use this gas of defects approach, right?
Yes, yes.
Yeah, so, well, at least the amplitudes that I mentioned for JT gravity, these 2-point functions, they seem to have a very simple generalization for these deformed dilaton potentials. The only thing that changes is you replace the density factors by the ones you find in these deformed models, and they were computed in several papers in the literature. These things like the 3J symbols, they don't change, apparently. At least for the class of dilaton. So these calculations were done for deformations of the dilaton potential, where the dilaton potential at large phi still goes back to the JT case. So that restriction has to be there, I think. But for those specific class of deformation of the dilaton potential, I think the answer is easily written down. You just write down the density factor. So instead of the Sinch function, you write down the function that was, well, written in one of those papers, and you find the answer for the boundary correlators, I think.
But to study, indeed, say, to interpolate between limits of usual Liouville in two-dimensional gravity and JT gravity, can it be done?
Well, the only thing that we understand are these deformations of the dilaton potential. So if you can write this in terms of a deformation of the dilaton potential, then yes. But yeah, if you're talking about more complicated objects in terms of the Ricci scalar, for instance, then, well,
not really. Just the old regime of 2D gravity, which was well studied in the 90s, 80s, 90s, and versus JT. Say correlation functions or even partition function which interpolates between two regimes. Both are solvable models.
Yeah,
it seems you have the means to just to have a single model to study both regimes.
Well, okay. These Liouville gravities, for instance, you can view them as pure gravity coupled to matter. Not JT gravity, but real gravity. So
okay, but then do you have an extra parameter? Can you have an extra parameter there which interpolates, which can bring you from this gravity to the JT gravity?
Well, if you think about, okay, I'm not sure if this is exactly what you would want, but if you think of these Liouville gravities as matter coupled to pure gravity, then there was a limit that takes you back to JT gravity, as I mentioned. But I'm not sure if this is really what you want or what you would want.
Okay, that was the first question. Sorry, just a technical comment. You compare it to the calculation of correlator in JT gravity to Wilson loop calculation, which was done in a few papers long ago for SUN case, of course, for the compact group. Your group is non-compact, SL2. But you probably can calculate also the higher point correlators using this analogy and character expansion. You can look at old papers like my with Mike Douglas and my with Jean-Marc Doll, where you use loop you use character expression plus loop equations, which can generate intersecting loops, also Wilson loops. I think it's an efficient way to compute higher point correlators. Certainly, some sort of loop equations should exist here as well.
But you're talking about more complicated things than a simple.
Yeah, for example, take two intersecting.
Yeah, precisely. So I didn't mention this, but this entire formalism, at least from the gauge theory perspective, it generalizes easily to more than one boundary anchored Wilson line and also intersecting ones. And using those, you can make contact to, well, out of time order correlation functions. For instance, you get them by these crossing Wilson lines. So if you have crossing Wilson lines, you get a 6J symbol coming from the intersection, and that 6J symbol, if you then apply this to the SL2R gravity case, that will be the thing that is encoding shockwave scattering.
But I mean, just technical thing that loop equations might be much easier than just 6G symbols, etc. You can generate the results in much more efficient way. Just
But
the
you're
advice
talking.
to look at these papers. Like the
Yeah.
names are Dole and myself. Then my paper with Mike Douglas, also the paper with Bulatov, all this in the 90s.
You're talking about a fixed topology still, or getting the sum over topology?
Say you have you have say a sphere. Your calculation is equivalent to the spherical, say the sphere and the Wilson loop on the sphere, because you have of course, you have not just a gauge theory. You have a chiral field, SL2 chiral field, as the boundary theory. So it's equivalent more or less. So you can compute Wilson loops with any self-intersections on the sphere. That works for SUN, but for SLN, I think the generalization can be also quite efficient.
So at the level of the disk, our calculations were exact. Okay, these loop equations, I guess they give you recursive
yes
formulas, right? But all at a fixed topology. So in the end, if you sum them, or if you know the entire series, then you should agree with the things or the calculations that I mentioned, I think.
No, I speak about correlators. Of course, some of the topologies is a more difficult issue.
Yeah.
Also possible. But...
Yeah. Well, these answers for the correlators are supposed to be exact. There's no approximation like a large n or something for a group or something like that made.
No, there also you can generalize any n these loop equations, and they can be efficiently solved in 2 dimensions. I have an old paper on it.
Okay. Yeah. Thanks.
Thank you. It was very interesting.
Thanks.
More questions? More questions from the audience? Questions?